I, Abhishek Misal, welcome you on the lecture on operational amplifier. The operational amplifier, often referred to as op-amp, stand as a fundamental component in linear circuit design. It is classical configuration. It comprises two input terminal, one that invert the single phase and another one that invert the single phase and another that maintain it along with an output terminal. The conventional symbol representing an op-amp is depicted in figure 1.1 with the due acknowledgement that with representation exclude the power supply terminal, which are undeniably essential for its proper functioning. The term op-amp is the widely accepted abbreviation for operational amplifier. This nomenclature finds its origin in the early stage of amplifier development, particularly during the era of analog computers. It's worth nothing that these early computers operated on analog principle as opposed to the digital computer. We are familiar with today the fundamental amplifier when integrated with a few external components enable the execution of diverse mathematical operations. An important application of analog computers emerged during World War II, where they play a pivotal role in the plotting trajectories for ordnance. Here basic definition of op-amp, that is called operational amplifier. Operational amplifier is an integrated circuit or discrete electronics component with two input terminal, that is inverting and non-inverting, one output terminal and power supply pin. It is designed to amplify the voltage difference between its two input terminal and produce an output voltage that is typically much higher than the input voltage. Op-amp are used in a wide range of electronics application, including amplification, signal conditioning, filtering and mathematical operations such as addition, subtraction, integration, differentiation. The key characteristic and feature of op-amps are: first, high gain. Op-amp typically have a very high voltage gain, often exclude 1 lakh. This means they can significantly increase the magnitude of an input voltage signal. Differential inputs. Op-amp have two input terminal, one inverting, it is a minus sign, and one non-inverting plus sign, allowing them to amplify the voltage difference between these two input. High input impedance. Op-amp present very high input impedance, which means they draw minimal current from the input source, making them suitable for interfacing with various sensors and sources without loading them. Low output impedance. Op-amp have low output impedance, allowing them to drive external load without significant voltage loss. Operational range. Op-amp typically require dual power supply, positive and negative, and operating within a specified voltage range. The most common power supply configuration are symmetrical plus minus VCC or single ended plus VCC or ground. Linear operation. Under normal operating condition, op-amp behave in a linear manner and their output voltage is proportional to the difference between the voltage applied to inverting and non-inverting input. Open loop and closed loop operation. Op-amp can be used in open loop configuration for high gain or in various closed loop configurations such as inverting amplifier, non-inverting amplifier, integrators, differentiators to perform specific function while controlling the gain. Op-amp are widely used in electronic circuit including audio amplifier, signal conditioning circuit, active filter, voltage follower and many other applications where precise and control amplification or signal processing is required. The versatility and performance make them fundamental component in analog and mixed signal electronic system. The block diagram of an operational amplifier typically consists of several key functional block and component. Here is a simplified block diagram of op-amp is shown here. The first stage is differential amplifier stage. The op-amp start with differential amplifier stage that has two input, the inverting input and non-inverting input. This stage amplifies the voltage difference between these two inputs. The next stage is gain stage. The output of the differential amplifier stage is connected to a gain stage. This stage amplifies the voltage from the differential amplifier, provide a high voltage gain. Output stage. The amplified signal from gain stage is passed to the output stage. The output stage is responsible for delivering the output voltage of op-amp. The next is power supply pin. Op-amp require power supply for operation. These are typically depreciated as VCC, positive supply voltage, and VEE, negative supply voltage, simply we call VCC and ground. The power supply pins provide the necessary voltage level for the op-amp to function. Feedback network. Op-amp often include a feedback network which can be external component like resistor and capacitor. The feedback network determine the op-amp's behavior and functionality. It is used to control the gain and other characteristic of op-amp circuit. Compensation and frequency compensation. Some op-amp may include internal compensation circuit to stabilize their performance, especially in high frequency application. This compensation is designed to prevent instability and oscillation. Offset null. Many op-amp features an offset null adjustment, which also include you to fine tune the output voltage to 0 when there is no input differential voltage. This is useful for minimizing DC offset error in the output. Protection circuitry. Some op-amp include protection circuitry to safeguard against over voltage or over voltage or over current conditions which can damage the op-amp. Input bias current compensation. Op-amp may have mechanism to compensate for input bias current that flow into their input, which can affect the accuracy of the amplification. Temperature compensation. In precision op-amp, temperature compensation circuit may be included to maintain constant performance over a range of temperature. Please note that the actual internal structure of a op-amp can be quite complex. Please note that the actual internal structure of an op-amp can be quite complex with multiple transistor, resistor and other component working together to achieve the desired characteristic. The simplified block diagram provide a high level overview of the main functional block in an op-amp. Different op-amp model and manufacturers may have variation in their internal structure and feature. So, it is essential to refer to the specific op-amp data sheet for detailed information. The circuit symbol of an operational amplifier is widely recognized representation used in electronic schematic and circuit diagram. An op-amp symbol consists of various elements that despite its essential characteristic below in the circuit symbol of an op-amp along with explanation of its terminal. The op-amp circuit symbol shown below. Now, we explain the op-amp terminal here. First is inverting input. This is the terminal marked with a minus sign. It is inverting input terminal where the input voltage to be amplified is applied. The op-amp amplifies the voltage difference between the inverting and non-inverting inputs. Non-inverting input, this is the terminal marked with a plus sign. It is the non-inverting input terminal. Here the reference voltage is applied. The op-amp compare the voltage at the inverting input to the voltage at the non-inverting input. Outputs, this terminal represent the output of operational amplifier. The amplify output voltage which is proportional to the voltage difference between inverting and non-inverting inputs is obtained from this terminal. Power supply pin, in the circuit symbol you may also see power supply pin represented as VCC and VE or VCC and ground, depending on whether the op-amp is powered with a dual supply configuration positive and negative voltage or single supply configuration positive voltage and ground. These pins provide the necessary voltage level for the op-amp to operate. First, offset null. Some op-amp may have additional terminal for offset null adjustment. These are used to fine tune the output voltage to 0 when there is no input differential voltage. The terminal are often labeled as offset or offset null. It is important to note that op-amp symbol may vary slightly depending on the schematic conversion or standard being used, but the essential element method above are generally consist. When working with op-amp circuit, it is essential to refer to the data sheet of the specific op-amp you are using to understand its pin output and electrical characteristic, as there are many different op-amp model available, each with its own specification. The IC 741 is commonly used operational amplifier with 8 pins. Here the pin diagram and brief explanation the function of each pin. The pin diagram of IC 741 shown below. In this pin diagram, these are the pin. first pin is offset null. This pin is used for offset voltage adjustment by connecting a potentiometer or resistor network between this pin and pin number 5 offset null. You can compensate for any offset voltage present in the op amp. Inverting input. This is the inverting input terminal where the input voltage to be amplified is applied. It is one of the inputs for op amp. Non-inverting input. This is the non-inverting input terminal where a reference voltage or signal is applied. It is the another input for the op amp. Negative power supply. This pin is connected to negative power supply voltage typically used in dual supply configuration. It provides the negative voltage required for the op amp's operation. In single supply configuration, it may be connected to ground. Offset null 2. This is the second pin used for offset voltage adjustment. It is connected to another end of potentiometer or resistor network used for offset adjustment, which is connected to pin 1 offset null. Output. This is the output terminal of op amp. The amplify output voltage which is proportional to voltage difference between the inverting and non-inverting input is obtained from this pin. Positive power supply. This pin is connected to positive power supply voltage typically used in dual supply configuration. It provides the positive voltage required for the op amp's operation. In single configuration, it may be connected to positive supply voltage NC, that is non connection. This pin is not internally connected to and it is left unconnected in the most application. It does not have a specific function in standard 741 op amp. Keep in the mind that while this pin out is typically for the 741 op amp, there are different variant package types of the 741. So, it is essential to consult the data sheet of the specific 741 op amp you are using to confirm the pin out and electrical characteristic as well as any additional feature or operation. Now, we are moving to the next step, that is called operation of op amp. The operational amplifier is based its high gain, high input impedance and differential amplification capabilities. Here a detailed explanation of how an op amp work. The first is differential amplification. At the core of an op amp's operation is its ability to amplify the voltage difference between its two input terminal, the inverting and non-inverting inputs. This means that it amplify the voltage applied to inverting input relative to the voltage at the non-inverting input. Ideal characteristic. In an ideal op amp amplifier, it has infinite input impedance, meaning it draw no current from the input source, effectively acting as an open circuit. It has infinite gain, often denoted as a ideal, which means it can amplify the voltage difference between its input to an extremely high degree. It has 0 output impedance, enabling it to drive external load without voltage loss. The input offset voltage, the voltage difference required to making the output 0 when input are shorted is 0. Input mode. Op-amp can be used in various configuration depending on the connection of their input. Inverting amplifier. When the input is applied to the inverting input, the output will be an inverted 180 degree or phase shifted version of the input amplified by a factor determined by the feedback resistor. Non-inverting amplifier. When the input is applied to the non-inverting input, the output will be non-inverted version of input. Amplify by a factor determined by feedback resistor. Differential amplifier. When the input is applied to both the inverting and non-inverting inputs, the output is proportional to the voltage difference between two inputs amplified by a factor determined by the feedback resistor. Voltage amplification. The amplification factor of an op-amp circuit is typically determined by the ratio of two resistors in the feedback network. For instance, in an inverting amplifier, A is equal to minus Rf upon R in, where A is the amplification factor, R is the resistance of the feedback resistor, R in is the resistance of input resistance. Negative feedback. Op-amp circuitry usually employ negative feedback, which means that a portion of the output voltage is feedback to the inverting input. Negative feedback stabilize the circuit, linearize its operation and set the gain to a desired value. Output voltage. The output voltage of an op-amp is given by CSS. Here the output voltage is V out is equal to A multiplied by V plus minus V minus, where the V out is the output voltage, A is the gain, V plus is voltage at the non inverting input, V minus is the voltage at inverting input. Sleeve rate and bandwidth. Op-amp have limitation such as infinite bandwidth, maximum frequency it can handle, and a sleeve rate, maximum rate of change of output voltage. These characteristics affect the performance in high frequency application. Real world op-amp amplifier have non-ideal characteristic, including finite input impedance, limited gain, input offset voltage, bias current and noise. Engineer must consider these factors when designing the circuit. The gain bandwidth product of an operational amplifier is an essential parameter that characterize its performance and behavior in various applications. To understand the gain bandwidth product, let us break down its meaning and implications. First, the gain bandwidth product. The definition of gain bandwidth product is the gain bandwidth product is representation the product of an op-amp open loop voltage gain A ideal or AOL and its bandwidth BW. It is often expressed in units like hertz and can be mathematically defined as GBW is equal to A ideal into bandwidth. A ideal or AOL, this is the open loop voltage gain of the op amp, ideally specified as infinite or very high in the case of ideal op amp. Bandwidth, this is the bandwidth of op amp which define the frequency range over which the op amp can operate linearly. Implication of gain, that is bandwidth product. Understanding the gain bandwidth product is crucial for designing an analysis of op amp circuit for the following reason. Duct implies an inverse relationship between the gain and bandwidth. In other words, as you are increase the gain of an op amp circuit, its bandwidth decrease and vice versa. Limitation on frequency response. The gain bandwidth product set the limit for the highest frequency at which an op amp can operate linearly. Beyond this frequency, the op amp gain began to decrease and the phase shift increased, resulting in distortion and instability. Practical consideration, real world op amp have limited gain bandwidth product. For example, if an op amp has a gain bandwidth product 1 megahertz, it can provide a gain 100 in the bracket 40 dB with a bandwidth of 10 kilohertz, or it can provide a gain of 10 dB, or it can provide a gain of 10 or 20 dB with a bandwidth of 100 kilohertz. Design trade off. When design op amp circuit, you often need to make trade off between the desired gain and the required bandwidth. You may need to reduce the gain to achieve a broader bandwidth or vice versa. For example, let us consider the concept. Suppose you have an op amp with a gain bandwidth product of 1 megahertz. If you want to design an amplifier with a gain of 100 or 40 dB, you can calculate the bandwidth using gain bandwidth product. The gain bandwidth product equation. Gain bandwidth product is equal to A ideal into bandwidth. 1 megahertz is equal to 100 into bandwidth, and bandwidth is equal to 1 megahertz upon 100, where bandwidth is equal to 10 kilohertz. In this example, to achieve a gain of 100, the bandwidth is limited to 10 kilohertz. Voltage feedback. The voltage feedback model for an operational amplifier is an idealized representation that amplify the behavior of op amp. For analysis and design purpose, it assumes the following characteristic: infinite input impedance. This means that the input terminal of the op amp draw no current from the source connected to them. It's effectively represent an infinite resistance to the input signal, ensuring that the input signal source remain unaffected. Infinite bandwidth. In this ideal model, the op amp has an infinite frequency response. It can amplify signal of an frequency without any distortion or attenuation. In reality, op amp have finite bandwidth and their performance decrease at high frequency. Infinite gain. The op amp is assumed to provide infinite voltage gain, meaning that it can amplify an input signal by an arbitrarily large factor. In practice, op-amp have high but finite gain, often exceeding 1 lakh or more. 0 output impedance. The output impedance of op-amp is considered to be 0. This implies that the op-amp can supply any amount of current to the load without affecting the output voltage. In real op-amp, the output impedance is very low, but not exactly 0. 0 power consumption. In this idealized model, the op-amp consume no power. It does not draw any current from power supply, making it extremely efficient. However, real op-amp do consume a small amount of power, although it is typically minimal. It is important to note that this idealized model simplify analysis and design, but does not exist in reality. Real world op-amps have limitation and imperfection is influenced by factors such as input bias current, offset voltage, noise and finite bandwidth. Ensuring use VFB model as a starting point for designing circuit with op-amps, but they must consider this real world limitation to ensure accurate and reliable operation in practical application. Operational amplifier can be used in different circuit configuration to perform various tasks, including amplification and signal conditioning. Two common configurations are the inverting and non-inverting amplifier configuration. Below I will explain both configuration and their respective equation. The first configuration is inverting amplifier configuration. The first configuration is inverting amplifier configuration. In the inverting amplifier configuration, the input signal is applied to the inverting input terminal of op-amp. The output is taken from the op-amp output terminal. This configuration provides an inverted version of the output signal, allow for adjustable voltage gain. The circuit diagram shown below. Now, the explanation of the circuit diagram. The first pin is V in. This is the input voltage you want to amplify, it is connected to the inverting input terminal. The second is R in. The resistor is connected between inverting input and ground. It determines the gain of the amplifier RF. This resistor is connected in the feedback path between inverting inputs and output. It determines the feedback impedance, further set the gain or the amplifier. V out, this is the output voltage of inverting amplifier. Gain equation, the voltage of the inverting amplifier is given by the ratio of RF to R in, with a negative sign indicating the inversion of the input signal. Non-inverting amplifier configuration. The non-inverting amplifier configuration, the input signal is applied to the non-inverting input terminal of op-amp. The output is taken from the op-amp output terminal, and this configuration provide a non-inverting output and allow for adjustable voltage gain. The circuit diagram shown below and their equation is also shown below, you can understand easily. Thank you for your listening and watching this video.